Okay, so projectile motion. We're just going to pick up where we left off from yesterday. But we'll just basically start it off. I'll give you everything today. So if you were away yesterday, it'll be given you, all to you today. Okay? So consider a projectile that's launched with an initial velocity of 50 meters per second at an angle of 60 degrees with the horizontal. So as you're copying this down, if you were away yesterday, please get the quiz before you leave. There was 2 we did yesterday, okay? Make sure you get them. Okay, so with most things in physics, you have to break them down into their vector components. Okay, so what you can draw is this 50 meters per second vector, okay, at an angle of 60 with the horizontal. So if you want to come grab a ruler, that's cool. Make your nice notes. Doesn't have to be perfect, you're right. So there is a vector made with the horizontal at 60 degrees roughly, and the vector has a value of 50 meters per second. So what we're going to want to do is break the vector into its 2 components, the x component and the y component. So there is the x component in red, and the y component in blue. And you can see the tail to tip nature of this vector, okay? It's so much to the right and so much up. Tail to tip, red for x, blue for yellow. Now if it's drawn like this, with this sort of, people in my math class, I call it the bow tie look, but this standard triangle where the vertical component corresponds to the sine of 60 and the horizontal component corresponds to the cos of 60. And you multiply by the hypotenuse, which is your resultant vector r. So we have r sine theta for this y component, okay? And we'll call it Vy. And down at the bottom we'll have this r cos theta, which we'll call Vx. Okay, so you can do this quite easily. So r cos theta would be 50 times cos 60, and this will give you a value of 25 meters per second to the right. And 50 sine 60 is going to give you your vertical component, 43 meters per second up. Okay, so the vector has been broken into its 2 components. Okay, so y. So the point of resolving the vector into its 2 components is because of dimension, really. You're going to have questions that involve horizontal and vertical displacements. So we have to be consistent with which part of the vector we are interested in. So if you're interested in a horizontal displacement, you're going to have to use the the horizontal component of the vector. If you're interested in a vertical displacement, you're going to have to use the vertical component of the vector. We have to stay consistent, okay? And there's also some others we're going to be interested in. The final vertical velocity. We're also going to be interested in the time to the peak, which is like the maximum height. And there's more. But the reason that we put into the two components is so that we can address specific questions. So it's just like the relative motion questions that we were doing yesterday, like the riverboat problem. Okay, if you're interested in a displacement in x, you have to use a velocity in x. Okay, so be consistent. So I'll put that here with you. Be consistent with your vectors. All right. Any questions so far? We're just sort of establishing the beginning of this. Is it okay if I move on? All right. Okay, so draw a man on the ground. Please go back. I deleted it all. Just kidding. So if you're waiting, you can draw a man on the ground and another man off to the side. He's going to throw a ball to him. That's the next picture. Okay. Sure. Okay, so we got a couple dudes here. This dude throws the ball up in the air, and this dude catches it. Okay, so there's an example of projectile motion. Projectile motion, we have only the influence of gravity, no other force. Once the projectile is launched, okay, in the air, we're not going to think about air resistance at all, and we're only going to be interested in this idealized situation where there's no wind and only gravity is acting. So this spot at the top we're going to call the peak, and this is your max height. So you could put in there, what color did I use for the vertical? Blue? Okay, so you can call this your maximum displacement in y. This is your maximum displacement in y. And then the other thing that we will talk about is if you have a displacement in y, you'll also have a displacement in x. Okay, so we'll call this one dx. And if you don't want to put the vector sign, that's okay too, because it gets annoying to draw that all the time. Okay, so you have your displacement in x and your displacement in y. That was bad. Okay, and what we call this displacement in x is the range. We call this the range. So sometimes on a test, if it might say find the range, what they're asking for is the displacement in x. So how far did the ball travel horizontally? And if they ask for the peak, they're asking for what was the maximum height that the ball reached. Okay. And just a note on this maximum height, because of this idealized situation, the path of the ball is completely symmetric and parabolic. So you have this symmetry, this parabolic path, so to speak. Okay, so the maximum height occurs, this maximum height occurs at the half time mark. So if it takes, 10 seconds for the one dude to catch the ball from pass from the other dude, the maximum height would happen at 5 seconds, halfway. And of course, it's idealized situation. And we can formalize that. So at the peak, the final velocity in the y component is 0. So is anybody confused by that? What does that mean? If I throw something up in the air, at the very top, what happens? In the vertical direction, right? So if I was to draw in these vectors, you'd have this velocity decreasing because gravity is working against it. And right here, there'd be no arrow at all. And then on the way down, you would have this symmetry. It would be the exact same speed on the opposite side, just in the opposite direction. So draw in these arrows because it demonstrates the symmetry. Okay, so at the beginning, that upward velocity matches at the end this downward velocity. It's the same speed, just opposite direction. Same here, and then in the middle at the peak, it's 0. It's completely flat if we're drawing a curve or a graph. Okay, so at the peak, VF is 0. We can use our gravity or our acceleration formula in y, of course. So A equals VF minus VI over t. This is our standard formula for acceleration. We know that VF is 0, so we'll have A equals negative VI over t. And t will equal negative VI over A, but A, of course, is just G. So all I did was cross multiply with the T and the A. And we know that A is gravity, so I just put that in there. Okay, so the time to get up anyway, the time to get all the way up to the top is going to be this formula here. And using like negative 9.81, the negatives will cancel. You get a positive value for time. And time total will equal 2 times time up. Okay, so if you wanted to get the time up, you could use this formula. So it's just the negative of the initial velocity divided by negative 9.81, and that will give you the time to get up to the maximum height. And if you wanted the total time, you would take this value and scale it by 2 because it's, halfway. Okay, any questions on that? Can I move on? Okay, let's go to the horizontal displacement. Okay, so we're going to start off with the fact that the horizontal displacement of a projectile is dependent upon the horizontal component of the initial velocity. And of course the time. But like how far is it going to go? Like the time is likely just a result of this, but how far is something going to move horizontally is completely dependent on how much speed you give it at the beginning, right? If I just push it like this versus if I just hammer it off the table, it's going to go flying, right? And the time is just a result of this. So completely the displacement depends on the initial velocity. And because gravity doesn't act left and right, and there's no other forces involved, there's no air resistance, then you get this very basic formula here. This is what we use for constant motion. Okay. Now the vertical displacement is also going to be dependent on the initial velocity, but different component, right? The vertical displacement is going to be dependent on the initial vertical velocity, so the y component of the velocity vector, okay? And there's also one other thing that it's dependent on, and that's of course the force due to gravity, which we are all aware of. If you ever watch a fail video, you almost just like laugh at gravity because it's so hilarious. I was watching that last night. Okay, so if you've ever watched somebody fall, it's because of gravity, and it's hilarious. And you're going to use this formula here, VIY. So it's the exact same formula that you're familiar with from one-dimensional kinematics, this VIT, but we're just going to put a little y in there because of this is displacement in y. Okay, and the rest, the rest of this formula is of course 1/2 AT squared, but we'll just slide in a g there for a, because we know that the acceleration is just the value 9.81 negative. So this is the go-to formula for your vertical displacement. And you got to be careful with this formula because t is the time to the peak. You got to be careful with this formula because we want the maximum displacement. You're going to use the half time mark. If it takes 10 seconds to catch the ball on the other side and you wanted the vertical displacement, you'd have to use a value of half of that. You'd have to use 5 seconds. Okay? And then of course g, everybody knows g, negative 9.81 meters per second per second. And you're only going to be given 2 types of projectile questions. One where you just like push a ball off a table, and the other one where you throw a ball up in the air. There's only 2 types. Okay, so we'll finish off this page of notes and then we will show you the 2 types. Just basically what to expect. And is that okay? Or go back? Are we good now?
Yeah, we're good.
Okay, so type 1 is just going to be a projectile with initial horizontal velocity only. And this is an easy thing to draw. You just draw like sort of a cliff or a table or whatever it is, and a ball or an object or whatever it is. And it has this initial velocity in x only. And you know, if you want to know what happens, just watch me push something off a table. It sort of has this curved, like, and it's called a parabolic shape. So what ends up happening as it hits the ground, maybe we'll put some water here. Okay. So what happens is, I'll just draw sort of the path that it takes. It sort of has this arcing shape like a parabola in math. Okay. Now what do you notice about those black arrows, those horizontal arrows? They're all the same, okay, and that indicates this constant motion in x. However, from experience, everybody knows that this ball is going to be speeding up towards the ground. So initially, when it's on the table or the cliff or whatever it is, it's 0, good. And then what happens is it will increase as it goes down. So that's why the arrows in the y are increasing. And then we have in blue this accelerated motion in y. Okay? And for this one, I'll just get you to put this in there. V I y equals 0. So that's the key for these problems. For these problems, the initial vertical velocity is 0, and it's just like the free fall question. If you remember, we did free fall a couple weeks ago. So if you go back a page in your notes, when you go to use this formula, this entire initial term just goes away. And it's quite nice. The whole term's just gone, okay, because of the VIY equal to 0. Okay, so that's going to be a skill that you're going to have to use. Now let's go to the second type. And this is where it gets a little bit more dicey. It's a little bit harder. And this is just a projectile launched at an angle to the ground. Just imagine like a cannon angled up and boom, it shoots. So a projectile launched, can't spell. And it's going to be at an angle to the horizontal. Okay, that word is horizontal. You can finish that off. I'm not going to. Okay, so draw yourself a ground. Draw yourself a little cannon. I'm going to omit that part. And the ball goes up in the air, and the ball comes down, whatever the object may be. I'm just going to sketch in the idealized path of the ball, this arcing parabolic shape. And notice that the ball lands, you know, where it took off. See how the displacement vertically never actually changed? So it's not like you're going to be shooting off a cliff and then it goes past where the cliff was and down farther. It's, I think 99%, I'm 99% sure that you're always going to have problems where it lands at the same height that it was launched. See how that works? So it'll always have this symmetric shape to it. So we can draw in the horizontal components of this motion, and you notice how it never changes. So you'll always have this constant motion horizontally. However, you will see that the initial velocities in the y shrink to 0, where at the top you get this like VFY equals 0 at this half time mark. And then you get this symmetry on the way down. And then, like, it depends where you want to call your VF. You could say your VF is here if you're trying to solve for like a max height, or you could say, you know, the VF is down here as well. It's just the VF is wherever you want it. So you could either have it in the middle or at the end. So the VIY, say let's just ignore that for now. Let's imagine that the VIY is right at the beginning and the VFY at the end. Notice the equivalence. So I'm going to put that in for you. VIY is equivalent to the negative of the VFY. So that's a crucial understanding for us. Very, very crucial understanding. So notice the symmetry. The initial velocity vertically is equivalent to the final velocity vertically, just in the opposite direction. Okay, so let's actually try and do some of this. The two problems, two situations. We'll do one horizontally and then the one at an angle. And then you'll be free to do homework and free to ask questions and so on. Are you guys okay? Do I need to? It's been a long week. Okay, example 1. Do you still need that page? Still need the page, Adel? Okay. Adel, you gotta stop with those funny faces on ENN. This whole thing, you're like... You gotta stop with that, man. I don't know. Just drives me crazy. You gotta keep it professional. Oh. It's very professional. It's very professional. Okay. Focus your attention on me. Hamza. Okay, a pool ball leaves a 0.6 meter high table with horizontal velocity 2.4 meters per second. Find time and horizontal displacement. Okay, look back in your notes. What is the formula for horizontal displacement? Please look back in your notes. Okay, one guy's got it. Who else has it? dx is what? Vx times t, the constant motion formula. Do we know Vx? Do we know t? Okay, so often t is the key to unlock these questions. Okay. Okay, you need to find t. That is your job. Okay. How to find t? Well, we got to use the other component. Okay. So use the y component. All this business here is like your x component stuff. We need to use the y component. How about 15 minutes? Okay. All right, so we got to go to the y coordinate here, or the y vectors. So what's our formula in y? dy equals what? Go back in the notes. It's also on your formula sheets, right? It's also on here, right from the kinematics first part. So what is it? And you do enough questions, you start to memorize these. VIY times t plus a 1/2 gt squared. Good. And initially, Emmanuel, What's the vertical displacement of this object initially? Adel, what is it? Initially, what's the vertical velocity? One person's got it. Kane, what is it? Initially, the vertical velocity of this thing. Oh, Hamza's got it. Swad, you got it? Is there any vertical motion when it's on a desk? Is there any horizontal motion? No. If I push it from the horizontal direction, is there any initial vertical? No, nothing. So this whole thing is gone. You have to know that one. It's the key. So then we have the vertical displacement is just 1/2 gt squared. Now we do some basic algebra. Times by 2 gets rid of half. Divide by g gets rid of g. Square root gets rid of square. Now, a lot of people are skipping this next step I've seen on the quizzes, and it's bothering me because it doesn't really show me what you know. You need to input the values, okay? So 2 times dy. dy is 0.6 negative. Do I need to draw a picture to show that? The ball is shot off like this. This is like your reference. So the displacement is negative 0.6 vertically. So 0.6 meters negative divided by negative 9.81. I typically omit the units because I just get lazy with doing it all the time. And we're going to square root this. And we'll get t. Once we have t, we can pump it back up into our formula for dx. Okay? So what do you guys get? Thank you, sir. So then we can go dx is equal to vx, which is 2.4 times the time that we just calculated. Thank you, Phelan, 0.35. And we get our horizontal displacement, which is what? So yeah, we've talked about this lots. If the displacement and the acceleration are in the same direction, you can keep them both positive, yeah. Or both negative, yeah. Just have to have the same sign. Yeah, time can never be negative, yeah. Final answer? And I'm not worried about sig digs right now, but I think it would be 0.8 if we use sig digs. Okay, so there is our horizontal displacement. And what do we call that again? Starts with R. No. No. Look in the notes. The horizontal displacement is called what? Wrong course, buddy. Okay, the range. All right. So, in summary, if we want a horizontal displacement, we got to use a vertical, or pardon me, start from scratch. If we want a horizontal displacement, I'll use my pointer. You have to use the horizontal velocity. Time is often what you need to unlock. Jump into the y component. Use the fact that it's a free fall question, so to speak. VIY is 0. This is gone. Solve for t. Pump it back into this, and you have what you want. All right, now we can try the harder one. Okay, example 2. Okay, a football is kicked with initial velocity (25 meters per second) at an angle of 45 degrees with the ground. Make sure you get this in your notes from the video, okay? Determine the time of flight the horizontal the horizontal displacement, aka the range, and the max height, aka the peak. Okay, so with this one, if it's kicked at an angle of 45 degrees, what's the first step? It was the very first thing I did in the notes. What's the language though? We need to resolve the vector into its components, okay? So you draw your vector. It was 25 meters per second. Again, this is the VR. This is the resultant velocity. And it's at 45 degrees to the horizontal. And we can resolve those into our two components. Whoops. Okay, so using sine theta and cos theta, we can get y and x respectively. So Vy is 25 sine 45. And if you're in my math class today, what do you expect these values to be? What do we know about the 45? Yep. So these, the vertical and the horizontal should be the what? Good. They should be the same, right? Okay, so 17.6776 for this one, and 17.6776 for this one. That's the only time it'll be the same, is when you have a 45, okay? Because of 45. So just some basic geometry. If this is 45, and this is a right angle 90, this also has to be 45. So that makes this isosceles. Good. So that means this side and this side have to be the same. Good. And that's the only time that will happen when they're the same, is when the angle's at 45. Okay? And the only reason I took so many decimal places is just so you guys know that when you round in between, you're going to have some error at the end. So what I always do is go to 4 decimal places, and you'll always be safe. I think even 3 decimal places, you'll probably be safe. But 4 for sure. Okay? Okay, so what we're going to do is we're going to just build a little chart. We're just going to build a little chart. And if you remember yesterday in the notes, in the workbook, they also did that. So we're just going to be consistent with our workbook. We're going to build a little chart. And we're going to say, okay, what do we know horizontally? So you could say X info if you wanted to be shorthand. Okay. So let's take a look at what we know. Do we know dx? Do we know dy? Or do we want to find that? Looks like they want both. So we don't know either of these. And do we know Vix? And do we know Vfx? Whoops, why did I do that? Thank you. So do we know Vix and Vfx? And do we know oh my gosh. now that it's up here, it'll be better. X on the left, Y on the right. Do we know the initial? Do we know the final? Question? Yep. Okay, do we know these? Do we know these? Yes, we do. What's VIX? This 17 point. I'm just going to round now. I'm not going to use my rounded answer in the calculator, but I'm just going to round for now, so it's easier to write. Do I know VFX? Katan. Do I know VFX? Does it ever change, the X component? No, so it's going to finish off at 17.7 as well. Okay. Now, what about vertically? Do we know the initial velocity vertically? Yeah, we would have to look at our vertical component, and it's the same. So this would obviously be different if it was numbers would be different if it was a different angle. Now, do we know it? What's the final y velocity? Is it the same? Ooh. Good. It's the same, but negative. And that's so key. It's so key that I told you to put a box around it and star it. I don't know if you guys remember that. Remember this? I told you to put a box around it and star it. That's this picture here. The initial velocity vertically, when you throw it up in the air, is going to be the same as when it comes crashing down. And some people are like, well, it stops at the end, so VF is 0. No. If VF was 0, then you could like jump out of an airplane and like land safely, which doesn't make any sense, right? So as the ball falls, it hits with a pretty big speed, right? Okay. Okay. So this right here is so critical, and it's due to the symmetry, in the motion. Due to symmetry of object's motion. And these ones over here is just this constant horizontal motion. Okay? And the last thing you can say is, well, if the x velocity never changed, the horizontal acceleration must be 0, and we know this already. And the vertical acceleration is, of course, going to be your force due to gravity. And that's all we know. Question? Yeah. This is all we know. All right, so let's try to solve the question. Okay, so A equals VF minus VI over T. Remember, the T is the key. That's easy to remember, right? The T is the key. Okay, so isolate for T. You get VF minus VI over A. Now, we have to be very, very clever. The final velocity will be this negative 17.7, and the initial velocity is positive 17.7. And the acceleration is due to gravity. So stare at that and make sure you remember that. If you don't remember that little trick, you'll never solve these problems. This is usually the go-to. So the final velocity, subtract the initial velocity. Notice the subtract in there. The formula dictates the subtract. It has to be subtract. When we substitute in, the final velocity on the way down is negative, and then VI is on the way up, so it's positive. So you're going to take a negative and subtract a positive. That becomes more negative, and then you're going to divide a negative by a negative, and like Hamza really wanted me to know, time is going to be positive. Okay? So do the top, somebody for me. It's like probably negative. Can you just do the top for me? Negative 30. Okay. Divided by negative 9.81, and we get a time of 3.6 seconds. This 3.6 seconds is the total time, okay? Because we were measuring the initial velocity and the final velocity relationship. So this is the total time. And this is all y component stuff. All this stuff is from the information on the y component of the chart. Okay? So we have the time, and that is the most important thing, the time. Next, let's find the horizontal displacement. That's really easy. Once you find the time, then it's just dx equals vx times t, and now we're into some x component business. So I'll show you a little separation. So we're solving for the range now. This 17.7, you would go into your chart and you would grab the x velocity. It just so happens to be the same value. So please don't get that mixed up. Might have been wiser to use a different angle. And the vx times the t, we got 63.7 meters. And this is our range. So that's how far horizontally it travels. And then back to some y component business. So I will erase this line. And let's find the max height, dy. Let's find the max height. Okay, so dy is equal to viy times t plus 1/2 gt squared. And if we're going to find the maximum height, look back in your notes, what value of time do we use? Half time? Kind of like a football reference, and it's a football question, right? So half time, that's an easy way to remember it. So if we want the vertical displacement, the maximum vertical displacement, and of course, if you had other times, you could find the vertical displacement at other times. But for the maximum height, you would use the half time. So initially, the VIY is the 17.7 number, and we're going to use half the time. So I think it was 3.6 total. So now 1.8. So I'll highlight that so it's clear. This half time. And then plus the 1/2. And this, Hamza, is where you be careful with your negatives. You absolutely put negative here, okay, sir? I got you. I'm almost done, like 2 minutes. 2 minutes. Okay? And I end up getting 15.9 meters. Okay? And that's it, you guys. Finito. We're finished. Okay? So in your workbook, you can look at question 2. It's similar to what I did. And then your homework will be on page 142, numbers 1 to... Yep. It goes to like 19. page 142, numbers 1 to 19. I'm not going to make you do all of them, so if you were to get a head start on that for Monday, I'll give you time on Monday to work on this. You know, maybe you do half over the weekend, get a good start on it, okay? Please don't show up with absolutely blank pages on Monday, okay? Okay, and then there's a leadership group here that wants to talk to you guys. So be quiet, please, and listen up.